Hello everyone, and welcome to the last tutorial slash class for ECE 457B. Today we're going to be taking another look at fuzzy inferencing systems with skfuzzy, and we will be tackling two of the problems or the examples in your lectures. So as usual, you gotta pull the repo or download the files and activate your virtual environment if you're using one. And go all the way to 08 fuzzy inferencing 2. And you're going to find two files. One is for comfort control. The other is the inverted pendulum control problem. I'm going to start off with the comfort control. So as usual, just a few of the libraries we're going to need. It's pretty much the same as the last tutorial. And over here, you see the problem statement that says that we have a temperature control system or comfort control system that has two inputs, basically the temperature and the humidity of the room, and we want to create a fuzzy controller that decides the cooling rate, the change in cooling rate that the air conditioner is providing. And as you can see here, this figure shows that you have two sensors in the room. The inputs go to the fuzzy controller, and then the output of the cooling rate goes to the air conditioner, which then responds to the system and provides a specific cooling rate or air of specific temperature later on. So we have temperature and humidity. We call them T and H as our variables, process variables, and these are provided logic controller. This determines cooling rate C. This is our third variable. And we want to maintain a particular comfort level inside the room. So we have temperature. For temperature, there are two fuzzy states, high and low, Hg and Lw. And they have their own membership functions, which we'll look into. And the humidity level has two other fuzzy states, also high and low, same name, but completely different membership functions, and they belong to a different fuzzy variable or process variable. So, and yeah, of course, the change in cooling rate can be positively high, positively low, negative high, or negative low, which basically means that we want to decrease the temperature a lot, decrease it a little, or actually increase it a lot or increase it a little. So negative high, negative low, positive high, positive low. This is cooling rate. So just think about it for a second there, because it could be a little bit confusing. And over here, we define the membership functions we're looking for. For that, this is, we can call it an expert system. However, you can think of it as your own room. I would define a high temperature as something that anything after 35 degrees. That's extremely hot, and it starts getting hot actually from 20 onward. So I would say this is my S membership function. Maybe it makes a bit more sense. And the low temperatures, it starts at 15. Anything below 15 is cold, and it reaches 0 at 0. It reaches 0. So basically, yeah, that was a mistake there. I got corrected down there as well. And then there is the relative humidity, which is an S membership function, 0.5, and it peaks at 1. And the Z member function for the low that starts decreasing at 0.5 and reaches 0 at 1.0. Okay, that's another, they're mixed up, or, these two wordings here are mixed up. I'm gonna fix that before I upload it anyways. So basically what we're looking to do is this here. So we can say something to this, or so the lecture did not show these, but we can see that this is, forget about the cooling rate. Over here, this is the temperature, this is the humidity, so we can say that this is high and this is low. So this is Z membership function that's 1 here and reaches 0 at, let's say, yeah, it reaches 0 at 1. Sorry, that is correct. So basically what we're looking to do is that this function here starts decreasing at, over here for our relative humidity, keeps at 1, starts decreasing at 0.5, and it reaches complete 0 at 1.0. Similar thing for the temperature, so it stays at 1 for low temperatures, it starts decreasing at 15, it stops being cold at 25. Okay, if that makes sense. Once we draw them or view the membership functions, it's gonna make more sense even. And then there's the cooling rate. So there's positively high, which is an S membership function from starts at 0.1, peaks at 0.8, this one. Second one, positively low, it's a triangular membership function. It goes from negative 0.2, peaks at 0.2 and stops at 0.8. This is similar, negative 0.8, negative 0.2, and then 0.2. This is, if you go here, this is negatively low, negative low, and this is negative high, just basically the opposite of these. So it starts increasing from 0.1 and negative 0.1 and peaks at negative 0.8. Anyways, we can take a look at how they look like. If we just skip here, this is basically low. So it's always low below 15, and then anything after that, it keeps decreasing, or the membership value keeps decreasing until 25, where it's no longer low. Same thing for this one, it starts increasing from 20. We can actually move this a bit. Let's say it starts increasing from 15 and or 17 and peaks at 30. So let's change that a bit. So 35 is extremely high temperature. So it's hot, but I'm gonna just make it 30. It's enough here. This is 17 to make more sense. And also maybe the temperature should go to negative 10 here. So I'm defining the universe here. So I'm using the same template I showed you last time. Basically, we have an initialization function which initializes the fuzzy system and then creates the system. And then we have some functions or methods to inference the model. Over here, we have 3 different universes for the 3 different variables. They're not the same universe. With temperature, we said it's from negative 10 to 40, the increment of 0.5. Humidity is from between 0 and 1, because I said it's relative humidity, so I can say it stops at 1, and the increment is 0.05, and then the cooling or the cool rate is between negative 1 and 1 with the increment of 0.1. So temperature, I define it as temperature, it's an antecedent. Humidity, it's the same. Each one of them has their own universe, and then the cool rate has the cool universe, and then you called it cool rate. So from there, we define the variables with their universes and everything, and their names. We need to define the membership functions themselves for each of them. So first we start the temperature. We said that can actually do this. We said that low temperature is anything below 15 is low. Once it starts reaching 15, it keeps decreasing until 25. So 25 is no longer low. So this is what I did here, 15 and 25 as that membership function to look something similar to this here. And then as membership function for high, which basically goes the other way around, and 17 and 30. Same thing for humidity, for a Z membership function that starts increasing at 0.5 and peaks at 1. Other one starts decreasing at 0.5 and peaks at 1 or reaches 0 at 1. And then the membership function for the cooling rate is we have positively high, positively low, negatively high, low, negatively high. We have positively high here is the S membership function, negatively high is the Z membership function. Each of them are the opposites, positively low and negatively low. Negative 0.2 to 0.2 is the peak, and then 0.8 is a triangular membership function here. Opposite for the negatively low, basically negative 0.8. It's a same thing, but in the negative direction, negative 0.8, negative 0.2, and 0.2. So now we defined all the membership functions. We go and I just store them in part of the class so I can use them elsewhere. This is just a visualization function. And then we set up the rules. We check the rules right here, and they're also mentioned in the lecture. So we can match them from here. Okay, so we have 4 rules. We say if temperature is high, humidity is high, then cooling rate is positively high, which makes sense if its temperature is high and it's pretty humid, then we want to get the room cooled faster. If temperature is high and humidity is low, then we still need it, but it's low. Temperature is low, humidity is high, then negatively low, we still need to fix the temperature but the opposite direction, because humidity is high, it could make you feel colder. And same thing here, if both are low, then negatively high, then we want to increase temperature significantly. Basically the same thing here. So if temperature is Hg and humidity is Hg, it's high, so the cooling rate is positively high. So high, low is positively low, low, high is negatively low, or negative low. And then low, high, low, low is negative high. Okay. And then we just create the system, as I mentioned, over here. So the system, which is the control system, sets up the rules, which I defined here, passes them to control system. I have now center control, and then create simulation, and then this is called self.center sim. And from here, I can just inference just passes these variables and computes the output, gives me the output, and returns it as part of this function. So we have this class, it's all ready now. Just run a few things. Make sure everything has run. Yep, and now run this. So now I've created fuzz system, which is an instance of that. You can visualize them. So you can see here that this goes from -10 all the way here, starts decreasing at 15, goes all the way to 25, and the other one from 17 to 30. And humidity. Sometimes you cannot see the full spectrum, but you get that this one peaks at 1 here, and this one reaches 0 as we expect it to. You can change that to see the full thing in the settings. And then fuzz system, cool rate. We have 4 fuzz systems, 2 triangular membership functions, and 1 Z membership function and S membership function. And basically that's it. We're done. We've created a system. Right now, Scikit Fuzzy uses Mamdani inferencing, which is what is required here. As you can see, we're using Mamdani inferencing model, and we're using the centroid method for the fuzzification. I'm going to show you in the next example how to change that, but it is right now centroid, so we need to change that at the moment. And once we do that, we just go. So it's as simple as just passing the variables. So passing 30, 0.9, pass that, we get a value of 0.6 here, which would lie mostly in one of these two. So we can say it's positively high because temperature is high, humidity is high, which makes a lot of sense. If you say that the temperature is actually 0 and the humidity is 0.1, we get a negative value here, which also makes sense, and it's 0.70, which is somewhere, say, around here, which is either negatively low or negatively high, which also makes sense in terms of what the cooling rate we expect is. So this is basically the example. It's as simple as defining the universe, defining the variables, and defining the rules here. You can use the same template uploaded before in the last tutorial. I just copy pasted it here and then changed a few things, and then I was able to do all that. So it makes it so much easier to read. We go to the next example, pendulum control. So again, same method. We import the same libraries, NumPy, Matplotlib, always there. It's by habit. They always import these. You never know when you'll need them. And skfuzzy, different parts of it with different names. And we have a new problem. We have something called an inverted pendulum. And the main idea here is that we are trying to make this pendulum here, called an inverted pendulum, stay straight up when it's on a trolley. So what we have control of is the DC motor here, which basically controls if the trolley moves right to left. And you can imagine that if there is a beam on your hand and you move forward, it would fall, or even a ruler, and you move forward, your hand quickly, it's going to fall backward. And if you move backward, it's going to move forward. And you can just try to balance it this way. So if it moves backward, you can counter the action by moving backward as well, and vice versa, which is basically the idea here. So right now, the pendulum is tilting to the right. The trolley has to move to the right to fix that and keep it upright again. So that's basically the idea. So we have two things to take into control into consideration, our two variables here. The process measurements are the angle of the inverted pendulum and the angular velocity of the inverted pendulum. And we say that the angle is between negative 30 and 30. So we can say that this is in degrees. Okay, not sure if this actually works. So it's in degrees. And we have this one in between negative 60 and 60. This is degree per second. And this is also degree per second. So this is the rate of change of the angle. And this is the angle. We have two fuzzy variable, it can be either positively high or positively low. These are our two states here, as defined somewhere around here. It's the same problem we had in the assignment. So we have positively large, positive, negative large, and positive large, negative large here as well. And for the control action, it can either be positive large, no change, or negative large. You can think of as moving to the right, not moving at all, or moving to the left. But it depends on how the DC motor is configured here, and so on. And the whole axes, but that's not our problem right now. Our main concern is how to create the fuzzy control system itself. So reading through the problem again, which gives us how we can define the membership functions. We have a direct fuzzy logic control, and we have ang and vel, which is angular position, angular velocity, and CNT is the current. So it's basically the control action. and it can be positive or negative. We say that the variable ang takes two fuzzy states, positively large and negatively large, and it's between support set negative 30 and 30, that's what we said here. So I defined it a little bit differently here. So over here, positive large is 0 for anything below negative 10. It starts going linearly from negative 10 to 20, and then it stays at 20, it's at 1 between 20 and 30. So basically 0 starts increasing linearly and then goes this way. We can define this using an ASP membership function. Negatively low is the opposite. It's 1, anything below negative 20, and then it starts decreasing to 0 linearly between negative 20 and 10, and after 10 it's 0. So you can imagine it going this way, which is basically a Z membership function here. Okay, so we can say that this one here goes like that, and this goes the opposite. That wasn't so linear, but you get the point. So we can imagine them to be S membership function and a Z membership function here. So for the variable velocity here, it takes same two states, and they're similar to these, but defined on a different support set. So we can say that they have the same thing, but between negative 60 and negative 20, 20 and 40, and 40 and 60 here, and same thing here. Just it's the same set, the same states, but on different support set, and the question mentions they're similar. So we have positive large, no change, and negative large here, and the membership functions defined between negative 3 and 3, and they're either trapezoidal or triangular. Positively large is also 0, before 0, and then starts increasing and peaks at 2. So it's still something that looks like that as membership function. The no control is 0, and then a bit below negative 2. Between negative 2, it goes all the way to the maximum at 0, and then it starts decreasing all the way to 2 and stays at 0 again. So basically a triangular membership function. So let me draw the axes here first, which goes like that. Okay, and this is negative 2a, and this is 2a, negative 2 and 2. This is 0 here. And then negatively low, it's 1, anything below negative 2, and then starts decreasing. So again, it's something similar to this here. And this is what we're looking for. So right now, again, imagine that. Let me just erase this part. And move on. Again, same exact thing. We have different universes. Negative 30, this time they're defined, negative 30 and 30. And then the increment is 1, negative 60 and 60, the increment is 1. And negative 3 and 3, the increment of 0.05. If you want the same number of values for all of them, you can do this. And for these two, and this one would follow because it's basically the same, just a different scale. And we have ang defined it here, antecedent, and the consequent is the control action. Again, you define all the universes and so on, and their names. And then this is something different that I mentioned here. So there are different defuzzification methods can be used. I've mentioned before the idea of going through documentation and seeing all the capabilities of the SK fuzzy library. Over here, we'll just take a quick look at the defuzzification method. So if you go here, the link here takes you to this point exactly. So you can see that dfuzz, which can be used separately, it takes 3 inputs here. If you want to use it separately, you can look at the documentation, but it also gives you the kind of options you have to use. So you can use centroid, bisector, mean of maxima, minimum of maximum, and max of maximum. So the default is centroid. So, and how you define this is just by going defuzzify method and defining the consequent is that. So over here we can say centroid MO1. For example, I'm going to show you that both work and both return different values, which should align with what you would do if you solve this problem by hand. So now we assign the membership functions. We have temperature membership function first. Sorry, this is angle. Again, I was using the same thing here, so it makes sense. Okay, and this is the control action, or CNT here, current. So we use the same universe. Just make sure you don't mess these up. If you switch them, things may give errors. So I just used that the first one said it's an S membership function, positively PL, positively large, that starts at -10 and then stops at 20, peaks at 20. This one is a 1 from -20 and then reaches 0 at 10. And same thing here. As I said, it's the same membership. It's the same. It's similar, but it has different support set. Over here, -40 and 20, -20 and 40 here. So the membership function for the control action here is, as again we said, it's S membership function between 0 and 2, triangular membership function that starts at -2, peaks at 0, and goes back to 0 at 2. And there's that membership function for negative low or negatively large. Yeah. It starts at -2 and reaches 0 at 0. Yeah, that is what it's mentioned here. And then again, the visualize function, setup rules, we're going to look into that in a minute. And we create the control system and we define the inputs and outputs here. These have to follow the same naming we used here. And then we define the output from here. So this should work right now. Take one more look at the rules, which I have written here. So if the angle is positively large and velocity is positively large, then the control action or the current is negatively low because we want to go in the opposite direction. If the angle is positively large and velocity is negatively large, then no control, because it's already going the other direction. We don't need to try to fix that. It's going to make it worse. If the angle is negatively large and velocity is positively large, again, it's already going in the other direction, achieving our goal. No need to do anything. And if the angle is negatively large and the velocity is negatively large, then we need to do action here. So it's PL, positively large, which is what we defined here. PL and PL is NL, PL and NL, no control. NL and PL, no control or no current. NL and NL is PL. And we return all the rules. And we basically use this to pass it to the control system here and create a simulation. And now our system is ready. So let's go all the way up, start running it. Okay, so now we have fuzz system, which is our system here. So we define this as the position or angle, basically. And we run that. And this is the angular velocity. That you see they're pretty much the same, just the values here are different, which going to make sense according to the problem statement. And then CNT here. It starts decreasing at -2, which is 0, starts increasing at 0, which is maximum at 2, -2, 0, and 2, which is exactly what you're looking for. And at this point, that's it. We're done. We need to just define the inputs and give it to the system, and it's going to do its magic here. Again, we're defining the current. So let's say our angle is 5 and -15. Run that. We have a very small value here. Actually, let's make it a little bit more prominent. Let's say it's 25. So the angle is large, and the angular velocity is also large. So let's say it's 40. You can see that the control action is -2.5, which is over here, which we see coincides with negatively large, as we expect. If we increase this even further, we're already at a maximum here. So, yep. And if we, let's say, again, the angle is large, but the velocity is, let's say, just 10, we expect this to be different. And again, now it's -1.99, something around here, so not the same value. We can follow one of these rules and see if they apply. So if the angle is negatively large and the velocity is positively large, or let's go with this, positively large and the velocity is negatively large. So this is 30 in the, let's say this is -40. See -1 point something 0, which is somewhere around here between the negatively large and the no action or no control. Oh, sorry about that, actually. Oh, it was the power -14, which means basically 0. So we have no control action for that. And you can follow these rules to make sure that they actually correspond, or when we give them to the fuzzy system, for the control system, they give us the output we expect, just to make sure that it runs more or less as we expect it to. And then from here, basically done. The system runs. We can try one more thing. Let's say it's 5 and actually 15, -40. I don't know, to be -10. Want a value that is small, but not that small. Okay. And then we can go ahead and change this here. So let's say instead of this, I go with centroid. No, the whole thing doesn't really make a difference except for this part. Just we run that, and we see that the value changed slightly, but it still did change. And again, it should correspond to what would happen if you did this by hand and use two different declassification methods. So this is basically the way we solve the two problems here. This is the assignment problem. I did not go through all of it, but I did give a hint on how to start solving that. It's a previous assignment, that's fine. And yeah, that's basically it for today. We went through how to use fuzzy systems and more detailed discussion of how to use this SK fuzzy library. It's open source in Python, and as I said, Python is encouraged to be used during this course in both machine learning and in fuzzy system because it's open source. You are again highly recommend that if you have MATLAB, go ahead and check out their fuzzy toolbox. It's more visual, much more visual than Python. It does basically the same functionalities, but you can actually see the inferencing similar to what you would see here. So you can actually see what's happening here if you have the fuzzy toolbox in MATLAB, which is more visually appealing and makes you understand more what's happening, and you can relate to what you do by hand a little bit more. But if you want the black box solution where you can change some parameters around, you can change the fuzzification method, defuzzification method, you can change your universe and so on, and see how easily you can change these and see the output. Maybe you change the rules, change the membership functions according to, because you think one of them isn't accurate enough, does not represent the reality of this process variable or consequent, you can do that. And yeah, I hope the tutorial was beneficial, and thank you so much.